So thank you for having me. It's great to be here and to listen to all the wonderful presentations earlier. So I think what I'm going to talk about will have a lot of intersections with what we have seen. So I will not discuss only like one specific approach or software for doing things. I will more try to give a taste of like what it looks like to build a story the way I do, using different tools that are typically freely available or open source. So I will explain two stories, as you mentioned, and I will just give briefly an overview of what Sentinel-2 is and how we use it in those examples. So I hope there will be some new things for everybody here and there. So first of all, regarding Sentinel-2, so it's one of a family of satellites, of Sentinels, from the European Space Agency under the Copernicus program. It's actually a constellation of 2 satellites launched in different years, and they host optical sensors, multispectral sensors. Because there are 2, we are able to get data like around 5 days, every 5 days from the same place on Earth. So that's really interesting. And what's really also amazing, as previously mentioned, the Landsat, the previous speaker, this data is also freely available for everybody. So just like Landsat, it's also an amazing data set. To give an idea of the resolution, I understood that probably most of you are familiar with hyperspectral data or maybe with ASTER. So here you can take a look at Sentinel-2 from that perspective, how different it is from what you know. So first of all, you have about 13, I don't want to say about, you have 13 bands, but sometimes we don't use them all. And each band has its own spatial resolution, and they reach 10 to 30 meters. So that's actually quite cool. Like Landsat was 30 meters here, 10 and 20 are a bit better. Regarding the spectral resolution, so when you talk about hyperspectral data, of course, this is multispectral, so you don't cover with narrow channels all the range of the electromagnetic spectrum that you're interested in, but we cover parts of it. You can see in the visible and the near infrared, you have quite a nice coverage of narrow bands, a bit better than ASTER even. But in the shortwave infrared, you have some limitations. So then depending on your application, of course, especially in geology, you can be a bit frustrated with some parts of what's applicable for Sentinel-2. But still, there are a lot of things that can be done. So I hope after the presentation, it gives you a few examples. If you want to take a look with a freely available tool at how different spectra would look according to the location of different bands of different spaceborne sensors, you can use the link below, and it's quite easy to have that as a first look on things. Now, the first story that I will go really very quickly through, so I'm really not going into the methods, but more on like how the tools were used. The work is already published in a paper I'm putting here if you would like more info, and of course you can contact me as well. And what's nice in context here is that actually this work was done in collaboration with CSIRO. So although we are in Europe and CSIRO is in Australia, and the work is actually in New Caledonia, that's the power of the new world. We can actually work all together and make a new story. So it's part of why I like all of this as well. So the story is in New Caledonia, just trying to map an outcrop. CSIRO had a lot of drill holes in a region that is a mining site, a nickel mining site. So with these drill holes that you have seen also earlier in the presentation, there were some reflectance spectra and analyzed samples. And close to the drill holes, there's an outcrop that has already been mapped using hyperspectral airborne data. So that's a little bit expensive. And we tried to see with Sentinel-2 and with the geological knowledge of the area, if we could redo that again, using the drill hole data. So it was a kind of a story like this. We started from the drill hole data. We resampled the spectra to look like those of Sentinel-2. With regression analysis, we tried to see if we could predict the mineral chemistry from the spectra once they are changed to Sentinel-2. When we got some models that we liked, we were able to to use the spectra from the image to map the data. So I'm not going again into all the methods, but I wanted to show you here a bit how things were done. So there was coding. I'm really excited after this presentation to try Orange. I don't know it, so to see how far we can go. But what's nice about coding in that sense is that also you can use a lot of packages that are available that were not even made for geoscientists, like this one that allows you to do pairwise correlations, but it was already it's done for psychological data research, for example, this package, Psych. Other packages are available like HSDAR to allow you to do the spectral resampling that I mentioned. So the hyperspectra, then you make them look like the Sentinel-2 data or other data. And then you also have a lot of nice packages that allow you to do the regression and compare different models and decide on one you want to choose. And for this work, we used the GLMNet package. For the applying everything on the imagery, we used data first to get the data. So it was not on the Open Data Cube, for example, which would make everything, of course, quite interesting. But here we were just using with single scenes. And it was downloaded from the French hub. The software that was used to pre-process briefly was Snap. This is a very powerful tool also that's really available from ESA. You can see here a bit of how it looks like below. And then the final maps were done using QGIS. The second, also very brief story I'm going to go through is the detection of small-scale mining. This is still also work in progress, so we hope to share with you something in the future. But we have already some things published that include what I'm going to talk about now. So I hope also, if you're interested, you can take a look at these, or again, contact me. The story takes place in Colombia. And you can see with the satellite image in the middle how these bright spots are. These are the small-scale mining areas, and they're quite dynamic. So we wanted to see if we can also detect them and do some temporal analysis to see if there are some patterns occurring on the behavior of the miners and so on. Lots of data was used from that is from freely available as well. Mostly we had some field visits to understand also the context. Just wanted to share a few sources that can help someone to make this kind of map that is available in the scene. So this is also done using QGIS. The data for borders of countries, you can find a lot on the HDX page. This is quite powerful. And the topography data, so that's available also freely from the Earth Explorer or from Snap. Snap is really great because when you open a scene, if it's georeferenced, it can already bring up for you directly for your site the data that you need. So that's also quite powerful. I'm sorry, I know that I'm a bit late, so I will try to finish as soon as possible. For how it looks like, the small-scale mining, it's like this. It's mainly bare soil with mining ponds. So we couldn't look only for the spectra. We had to also look for this kind of setting. So we did the classification, but also we did the post-classification approach to make sure we identify bare soil with ponds that would allow us to identify these mining areas. This was mostly done using Python. All the libraries that were mentioned earlier for the Open Data Cube were typically used here. And if you want to do some nice spectral plots, if in QGIS, you can also use the semi-automated plugin or the Hyperspec R package. So it allowed us to do a lot of temporal analysis to understand the change. And one nice package that we used that I will just mention briefly is the SPADE. It allows you to understand sequences in time and if there are some patterns. And this is a package originally used for sales, so for like people purchasing from the supermarket and so on, to understand how the sequences occur and if they are meaningful. And we were able to do that also to understand how the miners are behaving with this geospatial approach. The data was then shared with the stakeholders on MapX. If you would like to take a look at MapX, it's from the UNEP Grid Geneva, and it also is quite powerful for sharing. And that's mainly it. I wanted to mention briefly all these packages, and that you can use a lot of things that are not meant for geoscientists. And I think it's quite an exciting time for the geospatial community, especially also if you saw the Open Data Cube approach that brings the whole story into a very interesting world. Thank you.